Hi everyone. We'll start today's session. I hope you can hear me.
Yes, sir.
Yeah. Okay. Great. I think you can see my screen.
Yes, sir.
Yeah. Okay. So we'll be discussing some questions based on week 8 lectures. Let's start with the first question. Okay. Okay. Yeah. So we are given a pixel in RGB space, which is, this vector gives us three the values of the three colors R, G, and B. What is the corresponding value of the pixel in CMY space? So, what is CMY space?
Another model to represent a color.
Okay, okay, that's fine, but anything more?
It is a subtractive model.
Why do we need it when we have already
It is
RGB?
this is mainly used in printing.
Why? There's a reason for that. That's why I'm asking you why and why and why again. Okay, where is the RGB one used?
Display monitors.
So, when the display monitors are switched off, how does it look like?
Black.
So, black means zero, right?
Yes, sir.
By convention, it's taken as zero. So when you want to add colors on top of it, you need some additive model, right?
Yes, sir.
And RGB is an additive model. So that's why we use RGB for displays. RGB model for displays. Of course, nowadays we use slightly more complicated models so that we can visualize more colors. But yeah, it started with RGB. And what about CMY? You said that it's used for printing purposes. Why do you think so? CMY. Okay, how does printer print sheet look like? How does your general A4 size sheet look like?
White color.
Yeah. And what is CMY model? Subtractive model, you said, right?
Cyan, magenta, and yellow.
Yeah, this is, yeah, cyan, magenta. That's okay, but you said it's a subtractive model. So what are we subtracting here?
Subtracting from the white
Yeah,
color.
white color.
255 minus.
Yeah. So generally the print papers are white in color. So we would like to have something which subtracts the white part to get the desired color. So that's why we need CMY model for printers. So that's how these two models actually started. Rather, CMY was really started because of printing purposes. So both of them are linear, are in linear space. I hope you recognize that. Both are in linear space. So, well, answer to this question is very simple, but we should understand why this even exists. It's like take the maximum value per each per channel and then subtract it with RGB, which gives us the corresponding CMY channel. So C and R are complementary colors. M and G and Y and B. What do you mean by complementary colors? So when I add these two, they sum up to the maximum intensity value. Complementary colors, they sum up to the maximum intensity value. That's why they are called as complementary colors. Okay, so for this question, it's pretty simple. Uh, we have RGB as 100, 150, 90, which gives us what? 255 minus 100 is 155. 255 minus 150 is 105, and 255 minus 90 is 165. So this is the answer. It's pretty simple, but we should try to visualize it slightly more. Okay. So what I'll do is I'll take the diagram which was given in the class. So if R, G, and B are the three axes along which you measure the intensities for three colors respectively, then what can you say about this? So assume that change the color. This is the maximum intensity which gives us red. This is the maximum intensity which gives us green. This is the maximum intensity which gives us blue. Maximum in the sense for this case we have the maximum intensity is 255, but I'm writing it in general because you might want to scale it between 0 and 1 as well. Okay, so based on this, what can we do? We can just try to get a cube in this specific case. So what will be this point? What do you think would be this point?
White.
Yeah, because all three intensities are maximum: red, green, and blue. So you can think of this as 255 comma 0 comma 0, this as 0 comma 255 comma 0, and this as 0 comma 0 comma 255. It's just some corner of the cube. So why it will look like this, for instance. Okay, now where is CMY lying here? What is C? 1 minus, or rather maximum intensity y minus R, right?
Yes, sir.
So how do you think the axis will be defined? R is like this. So how? So 1 minus of that is something like, where should it be defined? So it's clear that it should be in the opposite direction of R, right? The CN axis.
Yes, sir. Opposite direction.
Okay, that's okay. But where should the origin be? Just if you see this equation, the origin here is this point, 255, 255, 255, and then you reverse the direction and go. I mean, go in the reverse direction of the respective color channels. That's all there is to it. So what does it mean here, geometrically speaking?
Origin is at white.
Yeah, origin is white, and we have to go in the negative direction of R.
Red.
Yeah, so
Yes.
R is in this direction, so we are going in this direction. This is what then? Cyan. Cyan. And the maximum intensity value for cyan will be, of course, in the corner of this cuboid, which will be given in RGB space. It will be 0 comma 255 comma 255, right? in RGB space.
Yes, sir.
Yeah. Okay. So where will the other axis lie? For instance, cyan is okay. Then magenta should go like this, right? And its maximum
Yes, sir.
intensity will be like this. And in RGB space, what will it look like? 255, 0,
255,0,250.
255. Yeah. And similarly for this one, this is what? Yellow. This is magenta M. Okay. So I hope you understand how it looks. Uh, since it's linear space, right? You can always try to map them in this. I mean, like a vector space.
Yes, sir.
So now it makes sense, right? Why are they complementary, geometrically speaking?
Yes, sir.
Okay. So yeah, there is nothing much in this question. It's just that you need to know this specific relation, and you don't even need to know that. If you know that they are complementary colors and they add up to the maximum intensity value, that's all there is. Any doubts? Okay. So I think I can move on to the next question. Again, we have the same intensity value out here, but then our question is slightly changed. Okay, so we are given the same RGB value out here, but then we have CIE chromaticity model, which is a model which can define all the visible colors out there that we humans can perceive. Okay, so we need to find the corresponding X, Y, and Z for the pixel P, which is this given by this RGB color in normalized XY chromaticity space, and we are given the transformation matrix as this. So what do we need to do? So if I consider this as T, and this is anyways, we are taking it as R, G, and B. How will XYZ look like?
But multiplication.
Yeah. So use the transformation matrix and then multiply it. Something like this.
Sir, the T is given by CIE people, right, sir?
Yes, yes, yes. Yeah.
Okay.
Okay, so we are given this transformation. Okay, I should replace it with values. What are the values? 100, 150, and 90. Okay, so given this, uh, okay, yeah. So given this, what should be the answer? Yeah, it's a simple matrix vector multiplication. It turns out to be something like this. Okay, so we now got the x, y, z values. What do we need to find? The x, y chromaticity in the small x, y chromaticity space. What is that small x, y chromaticity space? Do you remember something? Small x is given by. It's just normalization. There's nothing more to it. Normalization with the total sum of all the three channels x, y, z. So it turns out to be like this, which gives us approximately this. And for y, we just need to take the y channel and normalize it with the sum of all the channels, which is what 140.5. Sorry, oh yeah, 140.4 and then 344.5. This turns out to be nearly 0.407. Hopefully it's right. Okay. So why do we need this small x and small y space? What's the use?
Maybe converting the color in three-dimensional format to two-dimensional format.
Yeah, we want to convert it to two-dimensional format. But why aren't we computing the small z then equivalently? If I define some small z as this, let small z is okay. Sorry, small capital Z upon the sum of the three channels. Then why don't I define this? Why am I just satisfied with the two channels, small x and small y? Okay, first of all, we need two dimensions because we want to display it in the screen, right? So if I give a general user a three-dimensional cube and ask them to choose colors, might be difficult for them, right? So for general usage, you might prefer taking small x and small y because not everyone is particular about colors, apart from a few people in graphics or people who do photo or video editing. So in general, for general purpose usage, we just want everything to be mapped to two-dimensional space. So we defined x and y like this. But why z? I mean, why did we ignore z?
If we do a Z, we are not reducing. Again, it will be a three-dimension.
Okay, that's fine. But anything more than that? But aren't we losing anything? You might be thinking that we are losing information about z, right?
Yes, sir.
But actually, we aren't. Can you say why?
Maybe the chromaticity chart that was like okay,
Uh,
from CIE.
so if you see, total sum is 1, right?
Okay, yes, sir. Yes, sir.
Sum of this, and this. So if you input x and y, it will automatically compute z and compute the corresponding colors that was chosen by the user, right?
Yes, sir.
So we don't really need z to be computed because the total sum is 1. That's known to us. Okay. One more question. Do you think that this mapping is unique from capital XYZ to small xy? Do you think is it unique? Unique in the sense that if I give you a particular value of, I mean, if I give you two values of x, there does not exist two values of x, y, z such that they will give you the same small x, small y. Do you think is it possible? Hmm?
Maybe it is unique because the it's like XYZ is restricted to 0 to 255.
Well, XYZ is restricted to 0 to 55. Okay, that's not really the case. But yeah, the way X, Y, and Z are restricted in such a way that it gives us unique values for X and Y. In general, if you take X, Y, and Z varying from minus infinity to infinity, there can be multiple values of x, y, and z, which can map to the same small x and small y. One of the easiest example that you can see is just add k here, kx, kx, ky, kz. It will still give you the same x, right? The scaling doesn't matter
Yes,
at all.
sir.
Something similar to what we have looked into for the projective spaces, that we consider all points on the ray as the same point. I mean, all of them are equivalent. Similarly, in general, yes, there does not exist a unique mapping, but given that we have some restrictions on capital X, Y, and Z, we can actually get a unique mapping from capital X, Y, Z space to the small x, y space. Okay, so that's all there
Yes,
is
sir.
to it for this question. Any doubts? I mean, I'm just trying to give you a linear algebra perspective to this. That's all. Otherwise, the questions are pretty simple for the whole. I mean, for today's session, at least what I feel. Okay, so yeah, another question that we are given an RGB value, which is 30, 10, 20. What is the saturation value of this pixel in HSV color space? As usual, I'll ask what is HSV color space. What do you mean by HSV?
Saturation and
H,
hue, HUE.
yeah, hue, saturation, and value.
Value. Yes, sir.
Okay. So is it a linear space or a non-linear space? Well, it's a non-linear space. Okay. Why is it a non-linear space? I'll give you one mathematical reasoning of it. I mean, simply speaking, that if you have three different primary colors and you add them, it won't exactly be the value that will be represented in the HSV color space. So that's a non-linear space. So if you remember something like this, there was a circle drawn out here. Maybe I'll use shapes. Yeah, my circle was not even close to that so circle. Okay. So we have R, we have G somewhere here, and we have B somewhere here. So what do you think will lie here? Cyan, right? Complementary color
Yes,
scheme.
sir.
Yeah. For green,
Yeah.
magenta, and for blue,
White. White.
white. Okay. Yeah. So given this thing, it was told in the class, but anyways, I'll just try to revise it. So given this reference, the angle, the hue will be proportional to the angle. Hue is proportional to the angle made with red axis. I mean, red axis is the reference axis here, and the saturation is proportional to the magnitude along the direction. Okay. Uh, so if you remember, how do we calculate value? V. Just take the average of the three channels that we have, which is 30, 10, 20. Okay. Which gives us what? And what about the actual question, saturation? Saturation was asked, and if you remember the formula, this is like it's like this. So what is the minimum of 10, 30, 20? 10 by 20, so it gives us half. So this is that value. So given these equations, can you say why HSV model is a non-linear model, color model? Hmm?
Magnitude and angles are used. So
Ah, okay, that's okay. I mean, just see these equations. Can you say something with these equations?
one values depend. Like to calculate S, we are using V.
That's okay. Well, if you see this operator out here, is minimum a linear operator? Minimum is non-linear, right? Yes, no? Okay, what do you mean by linearity? So if x gives f of x, kx should give you k times f of x, right? The basic definition of linearity. So what is minimum out here? Minimum is uh, so minimum we have to consider at least we'll take two elements x and y. So if we scale the elements with the same factor, let it be for instance x. Okay, may not be the appropriate example. Okay, so the whole point I want to say is that minimum is a non-linear operator here, which gives you the non-linearity part here. So that's why you're mapping from a linear space to a non-linear space. I hope the basic idea is clear about HSV color space.
Yes, sir.
Okay. Okay. The next one is multiple choice question. So, which of the following is true for a CIE chromaticity chart? What is a CIE chromaticity chart? So, there is a chart something like this, where this represents R, there is somewhere in between which is G, and this is B, and we have axis somewhere here like this. X. So the small x is here, the small y is here that we defined earlier. And what else do you know about the chromaticity chart? If I call this as white point, where does it lie?
Point 0.5, comma point 0.5.
No. I mean, it's given in the option doesn't mean that it's right. It's actually 1 by 3 comma 1 by 3. Okay. And next is, what else do we have? We have a hue, which gives us the direction, and then we have saturation, which is given by, saturation is given by A by B. So if saturation is 1, it means that the color has maximum intensity along the hue. Okay. So given these things that we know, what are the things which should be right or wrong? Okay. The saturated colors are at the boundary, right or wrong?
It is at the corners. So
Uh, Not really. So if I pick a color, that means if I pick a direction, then what? I mean, this color is somewhere between red and green. Okay. So once you choose a color, then you have to define the saturation. So choosing a color means you are choosing a direction here, and then what is the maximum saturation that we can have given this definition? A by B. The maximum saturation will be 1, right? When max saturation equals 1, when A equals B. So when A equals B, then you are at the boundary, right?
yes, sir.
So this, the saturated colors are at the boundary, which is true. The next one is the white point lies at 0.5, 0.5.
False.
Yeah, it's false. Similarly, the fourth one is also
D.
false. Uh, in a simplified model, all colors on a straight line from the white point to a point in the boundary has the same spectral hue. Yes.
Yes, sir. It is one.
Yeah. So for the basic model that we are looking at, for the CI chromaticity model, yeah, it is true. So yeah. Any doubts in this question?
Sir, are we utilizing this chart in any mobile applications like that?
Um, if you have seen, I mean, there are some applications. I will not say mobile applications. So a few
Okay.
years back, I mean, I'm talking about a decade back, there used to be computer applications where you actually give user this chart, chromaticity chart,
Yes,
and
sir.
then they choose the colors. Of course, there are various versions of it now. Now you might have seen some hexagonal shape color chart or some other shape color chart. But this used
Okay.
to be the case. And they somehow mapped this whole thing to the
Hexagonal. Okay.
hexagonal or even a square. Depends on the company that they're, and their conventions. That's all. But this
Okay.
should be the underlying representation.
Uh-huh.
Yeah.
Yes, sir.
Okay. So we move on to the next question. Okay. So consider that the color of a source illuminant is represented by an RGB vector and the target color is given by this. So now given a color vector in the source image, compute the color vector using a diagonal correction rule. What are we trying to do here? Or what's the main objective? Yes, anyone? So what's happening is, so there is a source in the first image which has its own color, which is 150, 200, and 100. That is what is given here. And we want it to replace with a source which has color 150, 200, and 200. Okay, yeah. So that means we are trying to change the illumination color from one source to the other. So given that we have captured this image, this is this is captured. So we have intensity values for each color channel at every pixel. And we are given a color vector 100, 200, 100, which is captured at this particular position. So we need to find the corresponding color vector. If I try to change the source, illumination source. I hope the basic aim of this question is clear.
Yes, sir. So it's similar to the like the filters that come in mobile like this.
Uh, some of them, yes. I will not say
Some
all
of
of
them,
them.
yes.
Yeah.
Yes, yes, sir.
Okay. So, okay, now it's pretty straightforward. If you remember the formulas, there's nothing much to it. So, what does the diagonal correction rule says? Yeah. So we'll find the gain factors of the of each color channel. So source means I'll put it here, and this illumination source, which is actually our destination. So this is the destination illumination source. This is the given source. So this intensity values are given by RS, BS, and oh sorry, RGB, GS and BS, and this is given by RD, GD, and BD. Okay, fine. So yeah, so we just need to find the gain values, which is this is one KR KG is what, again it will be one KB is RB by BD by BS, which is 2. So once we get these gain values, what do you do? We get some factor F, KB times B. So RGB is what? Here this RGB corresponds to the color vector R, G, and B. So given a color vector RGB, we want to transform it. So we'll just replace the values. What were the values? 100, 200, 100, plus 100, 200, plus 2. So this gives us 0.8. Given that we have this, now we can go to the transform color, which I will write it as a RT. So RT is this one, RT, GT, and BT. Given that we have these three uh, destination color, what should it be? It is simply just FKR R. F is point 0.8. Here is 1. R is, put it right. R is 100. It is F kg into G, which is kg is also 1 and green is 200. Bt is Fkb into B. Gain factor here is 2, right? Yeah. 2 into 100. What does this turn out to be? This is 80, 160. This is also 160. Is this question clear?
Yes, sir.
So we're just trying to transform the original RGB into the new RGB. The new RGB based on the change of the source. That's all. Source of illumination. Yeah. Okay.
Sir, so if we like think about the real life thing, then this will be done for each and every pixel of the image, right, sir?
Yeah, yeah, yeah. Yes, yes, yes. Okay. So we are given the coordinates in the normalized XY chromaticity space, which we have been seeing for a few questions now. Given the coordinates of the three primary colors. So we're given three primary colors. Let's call it as RGB. 2 by 3, comma 1 by 3. G is 1 by 5, comma 3 by 4. G is 1, 6, 10, 1, 10. Okay. Compute the corresponding maximally saturated color in the XY chromaticity space, preserving the same hue and intensity for a given point. So let the point be denoted as Q, which is given as 0.31 and 0.27. And what do we know more? We know that our white lies somewhere here, right? Okay. Given all these things, I would like to draw a diagram like this. What is the smallest one? 1 by 6, 10. This is B. R will lie somewhere. Yeah. 3, 1 by 3. G will lie here. 1 by 5, 3 by 4. Okay. And our center that lies somewhere here. 1 by 3, 1 by 3. Okay. So given all these information, now we have some vector q, which is 0.31. So it will be slightly here and 0.27 somewhere here. So given this point q, okay, what is the maximum saturated color? Okay. So what do you? I mean, well, first we'll try to understand it geometrically, and then of course the formulas will make more sense and it will be clear. So how do we get the maximum saturated uh, intensity given the same? Oh, sorry, maximum saturated color given the same hue. So what does it mean? So we know this direction. Let's change the color down. Yeah. So we know this direction, and we just try to move along this direction. Here once, here this one more there, and also for the third one, if we extend it like this. So if we extend it like this, and we extend it like this, so these are the three intersection points. And the whole idea here is the intersection points gives us the maximum saturated color for each channel. Yeah. So okay, now this looks nice, I guess. Our origin might lie somewhere here. Okay, this is X and this is Y. Okay, great. So what we need to do, we need to find the points and the lines and the intersections. That's all there is to this question. I hope geometrically you have understood what does it mean to have a saturated color. Preserving the hue. So preserving the hue means we are preserving this direction.
So we need to find the maximum distance from all the three green points, sir.
We need to find the intersection points. That's all.
Okay. And in that, we need to select maximum.
Uh, I mean, it's a vector. You cannot have anything as maximum. So you can have three possible maximum combinations. I mean, three possible combinations where each one of them represents maximum saturation in the respective channel.
Okay, got it, sir.
Yeah. Directions is okay. So what do we need to do? Since we know some projective geometry concepts, we'll try to find the lines, corresponding lines, which is I'll just copy it from my notes. Yes, I should write this. So how will we get BG first? Okay, so we are trying to find the line BG first, which should be what? Given 2 points, how will you find the line? 1 6 1 10 1 cross product with 1 5 3 4 1, right?
Yes, sir.
So given this, we'll get something like this. So this is the BG line. So first we are computing lines. BG, BR, BR is this line, and with this line we again have to do the cross. I mean, we'll do the cross product form, and then we'll get something like this. So it's just taking cross product of the 2 points, which gives us the line. Again, GR will give something like this. So we now got the three lines. What do we do next? We need to find this QW. This is W, right? White point. So we need to find the QW line. The QW line will look something. I mean, again, we can just take the cross product and we get like this. Hopefully the numbers are right. Anyways, so given now these four lines that you have, what's the aim? You need to find the intersection points, right? So for finding intersection points, what do we do? Again, take
BG
a
cross W.
yeah. Again, take a cross product. Yeah. So we first get BG cross QW, which turns out to be 0.002 minus 0.002, 0.013 minus. Oh, no, there is no minus. Okay. So what can you say about this point? Are you done just by taking cross product? Yes, no, something. Would you lie in this 2D space with these three numbers? Hmm? What is the operation that we do for projection? Given a point, we keep the third coordinate as
Divide
1.
it by 1.
Yeah. So, okay. What do we do here? We divide it by the third coordinate, which gives us these values. And given these values, now we can embed this into the 2D space, right?
Yes, sir.
So, what do you think about these values? There is a positive value, there is a negative value, right?
Lies in different quadrant.
Okay, that's fine. I mean, it will like, I mean, like x is positive, y is negative means it will lie somewhere here. Yeah, x is positive, y is negative, it will lie somewhere here, right? Given the
Yes, sir.
yeah, okay. I hope my mouse pointer is visible. Else I think it will be very confusing for you. I think so. It's visible. Yeah. Okay. So it what can you say about this point? It's lying outside the triangle, right?
Yes, sir. Outside the triangle.
So is it a valid intersection point? I mean, rather this itself is the intersection point that we are looking at. You don't have to specify this. Yeah. You think it's a
No,
valid
sir. Not valid.
yeah. So it's not a valid saturation point. So we won't consider this point. Not a valid saturation point. Lies outside the triangle. Okay. So again we have other points as well. What can we do? GR into QW, GR cross QW, which gives us this. What can you say about this?
Valid point, sir.
Yeah, I mean it's a valid point because it will lie inside the triangle, comma one, valid point. And the third one will also look similar, which has value something like this. Gives us
Sir, your voice is not audible.
oh, okay, okay, yeah. I hope now it's better. Hello, can you hear me? Hello, I'm not getting any response. Well, anyone can respond. Can they hear me? My voice is not clear. Okay. Is it better now? Can you hear me? Hello? Hello? Arijit, can you hear me? Hello? Lakshman?
It's still not clear.
Okay. It's not clear. Okay. Um, I mean, how is it? I mean, is it breaking or is it low? Change the microphone settings, I guess. Now it should be slightly better. I don't know. Okay. We'll just do this question for now. I hope you can hear me. If you can't hear me, please interrupt me. So, which of the following statements are true? Image reconstruction using color demosaicing leads to sharp edges in an image. Do you think it's correct? What is color demosaicing? Uh, okay. Um, I, was it clear before? Just try. Hello. Is it better now? Okay. I don't know. I'm not getting any response.
Hello, now it's all clear, sir.
Okay. Okay. Yeah. It's good. Okay.
Yes.
I don't know what happened. I just unmuted and muted back. Okay. So yeah. So we have so image reconstruction using color demosaicing leads us to sharp edges in an image. Is it right or wrong? What is color demosaicing?
Mm.
Color demosaicing is what? So given what is this color filter array, right? Color filter array. That means we have some values like RG, and GB, for instance. If you are given some values like this, what is this that what is it that we want to do? We want to predict unknown colors at a given pixel. Rather, predict means I mean here to estimate. There is no prediction. Estimate unknown colors at the given pixel. That's all we need to do. So if you remember something like this, if I'm given a grid like this, for instance, and I choose a value here, for instance, I choose this pixel and I want to estimate green here. What do we do here?
taking average of the neighbor green colors.
Yeah. So take the average of the neighborhood green colors, which is the nearest four neighbors out here. So averaging leads to sharp edges or not?
No, sir.
Not sharp. Averaging is what? What kind of a filter is it?
Blur, blur filter.
Low pass filter.
Low pass filter.
Low pass due to averaging, which is low pass filter. So when we have low pass filters, we always blur the image. So we cannot expect it to sharpen the edges of an image. So this part is wrong. Okay. So green channel is less likely to be aliased. Is it right or wrong? Yeah, I think they are assuming here Bayer's model. So given Bayer's model, green channel is less likely to be aliased. True or false?
True, because we are using more green channels than
Yeah,
in
we
infrastructure.
record green in more pixels. Green in more pixels. What do you mean by aliasing? So more samples are there.
The averaging we do when like
No, no, no.
if no, not
If you
okay.
remember correct, I mean, if you remember somewhat like the sampling scheme, Nyquist sampling criteria, which, yeah, so we need a specific sampling rate. So, which should be, I mean, that sampling rate should be above than a given frequency. Sampling rate means some frequency at which you sample. That sampling frequency should be higher than the maximum frequency content present in the signal. For the given case, the signal is an image. So for this image, you need to know the highest, uh, what do you say? Yeah, highest sampling, I mean, highest frequency in the image, and then based on that, you need to sample all these colors R, G, and B. But the point is, we don't do it that way. We are directly assigning R, G, and RG, and RB, and RB without even understanding the underlying part, how much the frequency content is present in the image. So, given that we have slightly high frequency component in the image, aliasing means we the frequencies get mixed with each other. You can check for signal, I mean aliasing and signal processing, which gives you much better details. That when we sample, I mean at a lower frequency, which has high frequency content, then you get some artifacts which are not desirable. So since here the green channel is sampled more, so it is less likely to be aliased. That's all the reasoning is. I hope this is slightly clear.
Yes, sir.
Yeah, you have to check for the aliasing part from the signal processing aspect. Then it will be completely clear. Okay, so the CFA channel, in CFA, that means color filter array, something like this that we have. Green channels are sampled at a higher rate than red and blue. Is it true? I mean, yeah, by
Yes, sir.
definition we do.
Because
Why?
we use more green.
We use more green, but why? Humans perceive more green. Human perception of green is strong. Since our perception of green is strong, so if we sample more green, that means we'll have less error in the green channel. So since we have less error in the green channel, so most, I mean, we'll perceive as if the image is almost true to the original image. That's why we keep it, I mean, keep the green more sampled in the color filter array. Okay. Okay. The next question is, high correlation between red, green, and blue channels are very likely to have similar texture and edge locations. is very. Do you think it's right? Yeah, it's true. Based on that, we try to do that Laplacian kind of filter, right? Uh,
Yes, sir.
yeah. So we what do we assume that if we have gradients in one color channel, so we'll have similar gradients in the other color channel as well. So we take the second order gradients in the Laplacian based interpolation to get better values of the colors channels that are missing out here. So that's the main idea between using of Laplacian from the other color channels. So if you have high correlation, that means if you have an edge, for instance, in an image, so it should be reflected in all the three color channels. Yeah, maybe it's reflected slightly less in one channel and slightly more in another channel, but an edge will be an edge. So they have a similar texture. Since they'll have similar texture and the edge locations will also be same. That means if the locations are same, the gradients will also be similar. Well, the gradients will depends on the intensity value, but the direction of the gradient will be same. So given that the direction of gradients will be same, we can use that information to combine all the three channels to get more informative image. Is the idea clear?
Yes, sir.
Okay. Um, okay, then I guess we'll stop here. Any more questions on today's session?
Sir, the filter we use, like the base filter, sir, is it used in the near the camera sensor or in the display thing, sir?
It's mostly used for sensing part. It's not for the display part.
Sense.
Yeah,
Okay.
because sensing is pretty hard, right? I mean,
Yes, sir.
I mean, your sensor. How does a sensor work? It needs to detect different frequency range for it to actually absorb something and then uh, make a mark on it. So the frequency response, if it's low, I mean, you can have specific sensors where the frequency response is just given to the red area or green area or blue area. That means whenever a light comes of this frequency, it will, I mean, the corresponding sensor will light up and then it will generate the image. But having a general sensor which captures the whole light may not be the best optimal way to do it because the frequency response may not be uniform over all the whole visible spectrum out there. So it's generally used for the sensor part, and then once you have such images, we can interpolate it and get some good estimate of the actual image, and then we can use it during display time. For display time, we use all the three channels. I mean, all the three channel data is present out there.
Okay. And during display, maybe I guess blue is used more, so that's why we call a Blu-ray. Like, is it like that or?
Well, kind of not really the case, but I mean, we don't really have pure white out there. It's more
Yes, sir.
bluish, so that's why they call it as Blu-ray. Doesn't really
Blu-ray.
mean
Okay.
that we use more of blue of it.
Okay. At first, I thought because we use the green here more, so I thought why they're calling Blu-ray.
Okay,
I just
okay,
got confused with the display thing, so
okay.
now it's clear, sir.
Okay, any more questions on today's
That's all,
session?
sir.
Okay, I'll stop recording then.